Hi, my name is Dhruv Tyagi, and in this video, I'll be going over Unit 3 Energy of AP Physics 1. So to start, the first concept you need to know in energy is work. And work refers to the amount of energy that is transferred or exchanged within or out of a system by or via a force. Okay? So whenever we apply force over a certain distance, we're always either transferring in energy to a system or out from a system. And a system is what we define as the objects we're considering it, or the physics of in a environment. That's our system. The objects we consider the physics for in an environment. So the formula for work based on this definition is equal to force perpendicular times displacement s. And force is a vector, displacement is a vector, but work is a scalar. And the reason why is because we're doing the dot product of force times displacement, because we're taking the the parallel of force. And so the units for work, so you can think about the units for this, it's newtons times distance, which is meters. So Newton meters, which is equal to joules. So the unit for work is joules. And the idea with work is, again, positive work means you're adding energy to a system, while negative work means you're removing energy. So an example of negative work could be if we have a sled going this way and I'm pushing it the other way. I'm doing negative work, I'm applying a force at a distance this way, and therefore I'm doing negative work on it. Next, let's consider that the formula for work is force times distance. So work equals force times distance. And we know that force equals mass times acceleration. And we know that distance or displacement can equal to velocity final squared minus velocity initial squared over 2a based on kinematics. And so we plug that in. What happens is the accelerations cancel out. And if we expand, we're left with work is equal to mv final squared over 2 minus mv initial squared over 2. And this term here, mv squared over 2, this is known as kinetic energy, and it's given symbol k, and so k is equal to mv squared over 2. And what kinetic energy is the amount of energy you have from motion. So if I'm moving, I have a kinetic energy. I have energy that's called kinetic energy. And so we calculate it by using mv squared over 2. And so what this shows us the word kinetic energy term, which states that work is equal to the change in kinetic energy. So net work on a system, so all the work that's being applied on an object is equal to the change in kinetic energy. Next, we also have different types of energy. We have potential energy, which is given the symbol U. And in potential energy, most of them are conservative potential energies, which means that they're path independent. So what this means is that if we have an object, well, first of all, let me define what potential energy is. Potential energy is the energy given by an object's position. Okay, so based on the object's position, it has a certain amount of energy by the given symbol U. And there's two types of potential energy you need to know for AP Physics 1. There's many types, but the two you need to know is UG, which is gravitational potential energy, and US, which is spring potential energy. And so the formulas for each, UG is equal to mgh, and US is equal to k delta x squared over 2. And so the thing I was talking about before, path independent, means that no matter what path you take for UG, you're going to have the same amount of energy. So if I have this piece of paper here and I just go straight up, then I still have the same amount of energy than if I just like wiggled it around and went straight up. So no matter what path I take, the amount of energy is the same because it's path independent. It only matters how far the paper is away from the center of the Earth or from the Earth. Similarly for spring, It only matters how far the spring is pulled back away from its equilibrium position, which is what delta x represents. Delta x represents the distance from the equilibrium to where the object is being pulled back or compressed. And finally, we have the conservation of energy theorem, which states that delta k is equal to negative delta U in a closed system where no energy leaves or escapes. In other words, K2 minus K1 is equal to negative U2 plus U1 or UG2, UG1 minus US2 plus US1. So we can move the K to this side. We get K1 plus UG1 plus US1 is equal to K2 plus UG2 plus US2. And so what this shows us that in a closed system where no energy escapes, what happens is that the amount of energy the initial energy is equal to the final energy, okay? Because all these terms here represent our total amount of mechanical energy. All these terms here represent our total amount of final mechanical energy. And so the conservation of energy shows us that the initial energy equals the final energy as long as there are no external work terms, because a work term would be adding or removing energy. And so in a closed system, there's no external work out of the system. And this is the formula we can use to solve questions where there's no external work. Now, if there is external work, and let's say, for example, there's a friction or something, and there is being energy lost or added, we can add an external work term here. And now we can solve again like so. Because now we're accounting for this work, energy, being added or removed by adding this external work term. So these is the total energy, and we're adding this term to show, okay, it's not conservative, it's non-conservative, because some of the energy is being lost or added. And finally, one last topic you need to know is power, and power goes along with work. Power is the rate at which work occurs. So power is equal to work over time, or equal to the amount of energy that's going in the system over a certain amount of time. So basically just the amount of work being done in a certain amount of time, or the rate. And it's given the symbol, so joules per second, right? Which is given the symbol watts, or W, capital W. Power, if we think about it, work over time is the same thing as force times distance, right? Work is force times distance over time. So if we take this distance over time term, we know that distance over time is velocity, so work is also equal to force times velocity. So that's another way of expressing work. Or sorry, power. Power is also equal to force times velocity. Okay, so let's try out some practice problems now. So let's say that we have a sled that's being pulled on a flat ground at 30 degrees by a person exerting a force of 65 newtons, and we want to find out let's say it's also going a distance of 25 meters in 20 seconds, and we want to find out the power being done. So we know the power is equal to the net work over the time, so times 20, we need to find net work. So net work is equal to the sum of all the works, which is equal to the sum of all the perpendicular forces times their displacements. And so we consider the sled free body diagram. What we have is we have a force normal, a force gravitational, and a force tension from the string, or force applied, whatever. And so the only force that's perpendicular, the displacement, is in this direction, right? So these forces are not perpendicular, Fn or Fg. The only force that's being perpendicularly added in the direction of the displacement is this Ftx. Okay, because Fty is again being perpendicular. So the only force that's applying parallel, which is what our work term is looking for, is Ftx. And Ftx is equal to Ft cosine theta, which is 30 degrees. So cosine 30 degrees. So our net work is equal to the work done by Ftx, which is equal to Ft cosine 30 degrees times displacement, which is 25 meters. And so that's our term. And so now if we evaluate this expression and we divide it by 20 because that's our network term, and we want to find power. So this is equal to power. What we'll get is Ft is 65. 65 times cosine 30 times 25 over 20 should be 70.3 watts of power. So again, the way we approach this problem is we looked at the formula of power is work over time, and so we found the network, and then after we found the network, we just divided it by the amount of time, and we were able to find our answer. And we found the network by looking at all the forces being applied on the object and seeing which ones actually did work on it, because we saw that gravity or the normal force aren't doing any work on it because they're both being applied perpendicular to it. We know that work only applies if the force is being directed parallel to the displacement, when the only force that was doing that was Ftx. Okay, let's try another one. Let's say we have the problem like so. We have a spring connected to a mass, or like it's just attached, pushing a mass compressed, and it's compressed a distance of 0.2 meters from equilibrium. Call this equilibrium. And we want to know how far in height it goes up this ramp. So we also know, let's say we know the K is 250, and let's say the mass is 0.8 kilograms. So this is state 1. Let's call this state 1. Call this state up here state 2. So at state 1, what energies do we have? So it's not moving, so there's no kinetic energy. There's no gravitational energy, because let's say that so when we're using gravitational energy, we can say any point in our system is UG equals 0. So for simplicity, let's say that this bottom part is UG equals 0. So there's no gravitational energy here because we said that UG is equal to 0 at this point. So the only energy we have is kinetic energy from the spring being compressed. So kinetic energy is kx squared over 2, US1, right? And then this is equal to state 2, because again, there's no friction on the ramp. There's nothing in that, right? So there's no energy being lost. It's conserved. And so at state 2, it's going to be stationary because we want to find the max height. So once at its max height, it's going to be stationary. And there's no spring force. There's no springs. So the only energy we have is potential energy. And this potential energy is equal to mgh, because here our height is h, here it's 0. So delta h is equal to just h. So UG2 equals mgh. Now we can just solve for h, so h is equal to k x squared over 2mg, and we can just plug in our values. So 250, 0.2, 0.8, and if we plug it in, we should get that the height is 0.64 meters. So in the process here, we set up two states. We define where UG equals 0 is, and then we write our equation. We think about all the terms that would be in it. Well, actually, first we decide, is it going to be conserved or is there going to be external work? No external work, because in the system, right, this whole block, spring, earth system, there is no external work. And so we solved for it, and then we found that our height was 0.64 meters. Let's just say for another case, we have a ramp, and it goes like this, dips. Would our height change? And the answer is no, our height would not change, because again, energy, or UG and US are both terms that are path independent, which means the path doesn't matter, and so it goes to the same height no matter what type of ramp it looks like. And finally, let's see one more quick problem. This one's going to be a problem with external work. So let's say we have a ramp, we have an object, 1.5 kilograms. That ramp is 2 meters high, and there's friction at the bottom of the ramp as soon as it gets down, and it stops after 3 meters. So it stops here. Okay, so we want to find out what the coefficient of friction here is. So we know that there's going to be external work, so Wx. So we'll call it state 1, state 2, and we'll call this UG equals 0 at the ground. So there's going to be external work here. Here, it's starting from rest, so 0 kinetic energy, 0 spring energy. It's the only thing we have is potential energy. So UG1. Here we have nothing. If you think about it, we have no kinetic energy, no spring energy, and no gravitational energy because UG is 0 here. So we have 0 here. So if we arrange, we get that work external equals negative UG1. Now we can sub in our values. So the work external being applied is only friction. So the only work external is force of friction. So force of friction times distance, displacement, equals negative mgh. So delta h in this case is equal to 2 or negative 2 because we start from here. Our final is here is 0 and we start at 2. So delta h is negative 2. So we have that 2 mg is equal to force of friction times displacement. If we plug in the force of friction is equal to mu, or sorry, coefficient of friction times force normal times S equals 2 mg. And so we know that force normal is equal to mg, right here. We're not looking up here, we're looking up here because this is where the work is being applied. And so the force normal is equal to mg based on a free body diagram. So mg times S equals 2 mg. So the mg's cancel out. We're left with mu is equal to 2 times the displacement on land or on flat. And so the displacement is equal to 2 is equal to 3. So our coefficient of friction is 2/3 or 0.667. Okay, so the process here was similar to the process before, except now all we have to do is add an external work term, and we just have to, think about, okay, what does this external work term mean to find out what the coefficient of friction was. And that's how you solve energy questions for AP Physics 1. Thank you guys all for watching, and I'll see you guys all tomorrow. Bye.